Hello, good morning. Sorry for this. Let's start. There's a lot of material. I try to go fast, but make sure that you understand this work. Okay, so the idea is to develop a low power system and a scalable system with low added cost to detect or to be able to recognize gestures and dual touch location in the classical 4-wire resistive touch screens. So for those of you who don't know how these touch screens work, we have the screen and they have two layers of transparent conductive material, typically ITO, and we have these electrodes on the top and bottom screen, which are 90 degrees rotated. Okay, so basically we are going to apply voltage to one of the layers and then measure the voltage in one of the electrodes of the other layer. We are going to call the first layer active layer and the second layer passive layer. And then we change we then apply the supply to the other layer and we measure the voltage in one of the electrodes of the other layer. So when there is a contact, what we see is that we are measuring a voltage there which is proportional to the position that we are touching. So by doing these two phases, we are distinguishing the X and Y position of that single touch. Okay, so this is pretty well known, and this will be the simple model that we have here, where you realize that we have the same resistance crossing each of these two layers. Okay, so this is what we have a key point with single touch. The passive layer is basically an equipotential surface. There's no current flowing through it because the ADC is high impedance, so basically there's very low current and both electrodes are going to measure the same voltage. But when we are touching in two locations, we have two fingers, there is, let's say, more richness there. We have here a resistance there, we have the contact resistance, so these two electrodes are not going to measure the same voltage. In other words, this is not an equipotential surface, so there's information there that we can extract to get some extra information. Okay, we worked with screens that were classical and easy to use, that were not designed for this kind of applications. So it was quite a tough experimentation, and we made a lot of samples. The kind of gestures that you can detect with that are the classical zoom, pinch, rotation, or two-finger dragging. Okay, this is the kind of thing. Our idea is that we are going to measure the voltage in each of the electrodes, in all four electrodes, in each of the two phases. And for that information, we can detect these kind of patterns. For example, this is the voltage of the active layer. So when we are doing a pinch in the X direction, we see this variation and then this recovery here. When we have a pinch in the Y direction, this is what we see. This is what we see when we have a diagonal pinch. Both are showing an evolution, both active layers. When we have a diagonal, is the opposite movement. So basically, it's quite easy to make a state machine that can detect when we are doing these basic gestures, with just measuring the voltage with no hardware added, just a switch to check the 4 voltages involved. Rotations are slightly more complex. Rotations could be seen as a kind of zoom in both directions. So active layers, both of them show activity, and we have these kind of things, so we could detect a rotation quite easily. But the problem is that it's not easy to distinguish clockwise and counterclockwise rotation. And the way to distinguish that is to pay attention to what is happening in the passive layer. Okay, in the active layer, for example, there with that rotation clockwise, what we see is that we have in higher voltage initially in the left passive layer, and we have lower voltage in the right passive electrode of the passive layer, but that's changing with time. Okay, when we are doing the counterclockwise rotation, we are seeing the opposite in the passive layer. So this is what we are using to distinguish, to discriminate between clockwise and counterclockwise rotation. Okay, so there's a state machine that can be used for this. And the analysis can be done based on currents instead of voltage if for whatever reason that's more convenient for us. Just a comment, for detecting with precision a single touch, the best thing that you might have is a very low resistance in your switch. For detecting gestures, it's nicer to have a higher switch resistance. So you might have an extra switch depending on if you are looking for a single touch with high precision or just gestures. So the key point here is that this is extremely simple to add to any of the existing systems. So now we're going to deal with the problem of dual touch location. Okay, we could try to propose a model with equations, but these equations, there are a lot of them, they're non-linear. So if we want to put this in a low cost microcontroller, we're going to have issues with there. So we don't like that, and also there's another problem, is that the touch resistance is not constant. This is, for example, the touch resistance depending on your point, on your touch point, with very controlled procedure. Okay, so then we tried to tackle the problem in different ways. One of them is starting with a very coarse resolution, which basically is detecting the centroid of the touch and detecting the distance of the touch, which is very simple, the distance between the two touches and the angle. So then you can have an initial coarse estimation of it, and you can then refine it later on if needed. Another approach is to use a finite differences model of the screen, but that's very time consuming, and that's not good for microcontrollers. And another option that we evaluated is training an artificial neural network. Okay, so the coarse resolution works pretty well if you combine it with these equations or this finite model, because you can do an iterative process and increase precision if required. If you don't need more precision because you are in a screen that does not require high precision and you're just touching buttons or something like that, you can live with very low power. If you need more precision, you can run it several times. Okay, same with the finite difference model. And with the artificial network, what we did was to build a very simple artificial neural network that had 6 inputs that were the 2 voltage differences, which is equivalent to the 2 current of the active layers, and the 4 voltages that were measured in the passive layer, okay, in one passive layer and the other passive layers. And there were 4 outputs that corresponded to the coordinate of the 2 touches. Okay, we made, as is typical in this kind of things, we evaluated how many neurons we should put in the hidden layer, and we found that 5 neurons gave us good results. So it's not a very demanding neural network. And also, the other thing that we did was to avoid using the sigmoid, the classical sigmoid activation function, and just a piece linear approximation for it, and we achieved, let's say, good results for it. Again, it was trained. This is for example, the result that we have when we touch and we take the decision about where is the touch with that coarse approximation, finding the centroid, the separation between the touches and the angle, and this is a touch in controlled conditions. So you see that the accuracy can be good enough for many applications. Okay, this is another example. We touch in 2 different points and in 2 different angles. And these 2 angles, these are quite relevant because typically it can get confused. A lot of the screens, for example, in the first capacitive touch screens get confused with these rotations. Okay, these are the results obtained for artificial neural network in an ideal experiment, and I call ideal where we have a controlled force and a control point touching the surface and the point, so we know exactly how much force we are applying. The red circles are the true positions, and the estimated positions are the blue crosses. This is, for example, a result that we obtained with the artificial neural network on a real experiment, touching with a finger on top of a reticle that had the point marked there. And this is the error that we found in centimeters. And, And this is the result that we obtained in the training set, in the validation set, and in the test set which was not, let's say, these were touches that were not exposed before, okay? So this is the variance, the sigma of the error. So as you can obtain, this can be less than 0.1 centimeters in sigma, which can be more than enough in many applications. Okay, so I will just conclude with the conclusions. We have presented here a couple of things, couple of ideas. First was a basic way to distinguish two touch gestures with basically the same hardware that we have available for 4-wire screens and with existing screens. So the other thing that we have discussed is how to use these screens with a bit more computing and processing to try to find the dual touch, the location of dual touches. And we have proposed several ways to sort it, and these are the results, for example, that we obtained with an artificial neural model after training a screen. So that's basically all. Thank you very much for your attention. So, sorry, can you repeat?
Yes, can you address the additional delay in the algorithm with the artificial network versus the traditional hardware solution?
No, I mean, it's what I found is the basic problem with the artificial neural network is I mean that I don't see that very practical in a consumer application if you have to train that. I mean, it has good potential. The idea by proposing the artificial neural network, the hardware is really simple, but you need that training. So it could be good if you could have the system learning based on certain situations where you have in the screen information that is well controlled and you are expecting the user to touch the OK or two buttons that you know where they are. So then you learn if you're causing any error, and you can train the artificial network. The user itself can train the artificial network without having an initial stage where you have to train it. If that's not happening, then what I will go with that coarse approximation and then just feeding it through the model 1 or 2 times if needed, just to get the right accuracy depending on the context that you are at in the system. And that's basically, it has a slightly more complexity than the solution with the ANN, but very affordable for any baseband processor. Yeah, with what I have presented here, you will with 3 touches, you will drive the system mad, definitely, because this is using. I mean, if you want to deal with that, you need just to build that slightly differently so that you have more measurement points, not just 2 electrodes. I mean, and that could be easily to be done, but that means redesigning the resistive touchscreen. Thank you. Thank you.